Okay, so when you look at the AP test and all of its topics, the biggest thing that stands out for BC is arc length in all of the realms. Because we have arc length in various settings, right? Regular, parametric, polar. And sequences and series. Okay? Yes, we have like the different ways to integrate, and those are sprinkled throughout. But probably the heaviest topics you are going to see appear consistently are the arc length and the sequences and series topics. Okay? Now, today we're going to talk about sequences, and it's a pretty minor portion of the entire chapter, but it's kind of our foundation before we talk about series. Okay? So what's the difference between a sequence and a series? What? Thank you.
To get basic stuff out of the way.
What is a sequence? A list of numbers, a pattern. Okay? We actually, in math, we're going to say that it is a function that gives us a list of numbers whose domain would be the integers. Right? What's the most famous sequence you know? Fibonacci. Okay? Has anybody seen the movie 21?
I just watched that.
Okay, so you know how on the birthday cake they have the Fibonacci sequence?
Yeah.
And then 21's blank? Like, I cannot wait to do that for my husband's birthday when he turns, well, what comes after 21? 36, right? Isn't it 15?
34.
34.
34.
Which is next year. I'm so excited.
That's so weird. I literally watched it this weekend.
Wait, no. That's this year. I should really know how old people are. Okay. Yep. Okay. So a sequence is a list of numbers is what we like to think of. A series is the summation of that list of numbers. Okay? We'll get there tomorrow.
Okay.
And really for 2 weeks, like all of next week and all of Valentine's week, we're going to talk about different ways to determine whether our series that are infinite add up to a number or not. Okay? When we talk about sequences and then eventually series, okay, instead of using x, we're going to use the variable n. So sometimes you will see this notation, but most times you are going to see this notation for a sequence. And if you flash back to pre-calc, this is the same notation we used in pre-calc. What? Arbitrary. Oh, if you go into like pure mathematics, you get to use arbitrary all the time. Yes.
If its domain is only the set of positive integers, then it's just a piecewise function because then it's only at 0, 1, 2. So
It's basically dots.
So yeah, it's not even a function.
It's a function,
Oh, God.
but it's not a curve.
It's not continuous.
It's definitely not continuous. So you do have like a sequence mode in your calculator, and if you were to put a sequence in your calculator while in sequence mode, it would just graph dots, like Joe was describing. Okay, so here are some examples of sequences. Don't write them down because we're going to look at these individually, okay? But here's just a variety of sequences, and we're going to talk about whether these sequences converge or not, and then we're going to start talking about whether our series converge or not, okay?
As in if they actually add up to something or if they're infinity.
Yes.
Oh, no, the first one.
Okay, so our first theorem.
Limits
taking the limit of its rule. So if our sequence is n, then we take the limit as n approaches infinity of n. Okay, we literally just take the limit. Okay. When we
Special practice.
what? Do you just okay? Are you just making random comments to
Yes, I'm
yourself?
sorry.
Should I just assume that you don't have a question?
No.
Okay. Gabe will be talking to himself throughout the remainder of the period. If we actually get a number, then the sequence converges to that number. If we get infinity or doesn't exist, then that means the sequence diverges. You're going to see infinity happen more often than doesn't exist. But if you imagine like a sequence like 2, 4, 6, 8, 10, 12, that's just going to keep growing and growing and growing and growing and growing. So it's diverging because it just continues to grow and grow and grow and grow and grow. I'll come back to this. Converging, like if we have a limit that is a number, we say that it converges to that number. And I'll show you what that looks like. But basically, if we can attach a value to the limit, then our values are getting closer and closer and closer to that number as we continue throughout our sequence. Okay? Now, I don't think you need to write this down, but I'll show it to you because it's in our book. Well, maybe. If you keep touching it, it changes colors, which is sometimes kind of fun. But you know how to take the limit of a function, right? So if you imagine our rules for taking limits as like functions like curves, they're going to be the same as when we're taking limits of sequences, okay? The domain being positive integers isn't really going to affect how we evaluate the limits, okay? So let's look at some of the sequences that were on my first slide. Not all of them, but some of them. This one, 1/2, 2/3, 3/4, 4/5, 5/6, 6/7. Go ahead and write it down. If our domain is positive integers, how could we describe the rule to this sequence? N over n plus 1. So if we take the limit as n approaches infinity of a sub n, which I'm just going to go ahead and write n over n plus 1. That's a lot easier for us to determine what our limit would be. Towards infinity, what is this going to approach?
Infinity over infinity.
Okay, so we need to think of something else. So you can either think of L'Hopital's rule or our horizontal asymptote rules. Either way, we get 1. Do you have a question?
Good.
Derivative of n is 1 over derivative of n plus 1 is 1. Okay, so we say that our sequence, a sub n, converges to 1.
That was so hard.
That's confusing though, because 1/2 plus 2/3 is greater than 1.
We're not talking about the sum. We are talking about the sequence itself. So if you think about plotting these
Oh, what
coordinates.
the last number?
It's like
Yeah.
2 billion over 2 billion and 1.
right, if you think about the little dots that we would plot, they're going to get closer and closer to 1. Okay. Now, Joe, tomorrow we'll start talking about adding them
Okay.
together. Which
I can go without sigmas today. It would make my life much easier.
there will be no sigmas today.
It's fantastic.
But for like the
Yeah.
next month, you'll have lots of sigmas.
Every day though.
From tomorrow to all the way
It's like the
through
worst symbol.
March 8th,
It's like
you will have sigmas.
when an algebra 2 student is, I'm like tutoring them, they roll up with a worksheet on summations. I'm like, oh, sorry fam, can't help you out here.
One third, 1/3, 1/9, 1/27, 1/81st. Oh, it keeps going. Sorry. 1/243. What's our rule?
1/3 to the n.
So what do you have if you're starting with 1 or 0?
You always start by plugging in 1.
Oh, okay.
So we would have to make this 1/3 to the n minus 1, so that when you plug in 1, you get the 3 to the 0. Okay? So now let's take the limit of a sub n. What happens in our limit when we have 1/infinity?
It equals 0.
So this sequence converges to 0. Okay, now I'm going to go back to that slide where I had a list. Can anybody point out a sequence that would diverge?
The last one
The last one,
and the first one.
this last one right here is -1 to the n minus 1, we'll say. It goes 1, -1, 1, -1. Okay, that oscillates without changing at all. So that is going to be a diverging, sequence. What other one?
The top one.
Okay, the first one, this rule would be 2 to the n minus 1. That limit is infinity, so that sequence would diverge.
So fractions are your friend. I mean, diverging means you have to do less work.
Okay. So over here, when we talked about this, if we have a function that has a limit, then that means our sequence will have a limit. The converse of that is not true. If our sequence has a limit, that doesn't necessarily mean that our function will have a limit. Okay? Because remember, we're working with every value versus only positive integers. Okay? So things could be happening in between the positive integers that would cause something like a function not to have a limit, but the sequence could. Does that make sense?
Yeah.
Okay? For example, and I don't want to spend a lot of time talking about this, but the limit towards this guy wouldn't exist. However, the sequence is 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7.
Because the sign of pi over n is always going to be 0.
Exactly right. The sign of pi over n is always going to be 0 when we're talking about the integers, but when we're talking about all real numbers, it doesn't work out so much. Okay? But you won't have to worry about that.
If It's the sine of pi, not pi over.
Well, it's 1 over n plus the sine of pi n. So every time I plug in n, this goes to 0, and you just have 1 over 1, 1 over 2, 1 over 3.
Oh,
Because this will always go to 0.
Oh, because they're integers. I'm like, what?
Yeah. Okay, let's talk about some limit properties. You may or may not need to actually write these down. I'll let that be up to you. But I want to officially talk about these so you are aware. If we have a sequence that has a coefficient, it is okay to take the limit of the sequence without the coefficient and then multiply it.
How did we just start capitalizing the L?
Okay.
Just like
So here's the deal.
It is resonated with me.
When I originally made this a few years ago, it like automatically capitalized it, but I can't really go back and edit it because of the change in whatever. Yeah. So
Ugh.
make them lowercase in your notes.
No, because see what keeps happening is then I'll like write LIM, a zone.
Stop zoning. Focus.
I saw your Lima stones at work yesterday.
I was trying Lima stones at work the other day.
Oh, I
I
was
was on the
like,
notepad
I
and I
don't
was
know
like,
what we were talking
hey,
about.
ladies.
Honestly, I was complaining to Lauren.
About math.
Maybe.
Okay.
Sorry, let's continue.
Okay. Adding, subtracting, multiplying, and dividing can be separated with our limits just like it was with functions.
Other things, not so much.
What?
Like with derivatives, right? Like, can you do derivatives in series? Or
Just wait.
that's the question.
If you can use L'Hopital's rule, you can easily use a derivative. Because L'Hopital's rule requires you to derive.
Well, we're going to talk about a derivative and what it could tell us about our sequence. Okay?
What, like the change of the pattern?
First problem, I want better to like identify the sequence.
I mean, we have two.
I think it was like 13 or 14. Find the difference, and then find the difference again.
yeah.
Keep going back until you got constant. Oh,
Victoria,
good
you are
God.
making me so stressed right now.
Just casually written those in.
It's the same rules as like logarithms.
Just gonna write them down so it makes me feel special. My trash can blew this morning. I picked it up, pulled the trash back in the break. Sad. I was like, you know what? This would happen.
But you know what, Gabe? You have somebody that comes and collects your trash, and you don't have to take it anywhere. So that is a wonderful thing, isn't it?
It's pretty good.
Hang on.
I hope you're gone next year on
No, I
this
really
day.
don't. That,
Well, this could get shared with the Monarch kids because
Yes,
they're
better.
gone today.
Oh.
Yeah.
Hi,
So,
Monarchs! Can we have a code?
Y'all are
for
cool.
Monarchs?
I don't know if
4 or 5 of
he'll,
you.
I don't know if he'll share it or not.
You
I just said it could be.
Ooh, gross.
Okay. So code word trash.
Don't read into it too much.
That's just for Gabe complaining about his trash. Okay. We never say that. Don't write this down. Let's just check. Okay, we chatted a little bit about it. We don't say that a sequence converges to infinity. Instead, we say that it diverges. Okay.
I'm gonna write. That's like.
A sequence doesn't necessarily need to diverge to infinity in order to be able to diverge. Because of this sequence right here that we pointed out on that first slide, 1, -1, 1, -1, 1, -1, its limit is not infinity, but it also doesn't converge. It doesn't have a limit. The limit doesn't exist.
It's
I
like,
think average all the
do you know the concept of super actions or whatever? There was a weird concept where, like, if you repeat something infinitely and then stop, like, it won't work. It was a video about how you can have infinite surface area with a finite volume, and it got into super actions where, like, if you infinitely turned a lamp on and off and you stopped, would it be on or off? Well, you can't answer
Philosophy.
that. You can't answer that because it diverges as a mathematic sequence.
Oh, interesting.
That was the whole.
I never thought about that as a lamp turning on and off. Okay. That was interesting.
The light.
Okay, monotonic. This is something you talked about for like 5 minutes in AB. Calc AB.
Oh.
Probably. A monotonic sequence means either
It's really boring.
right.
Non-decreasing. Wouldn't that be increasing?
No.
I want to see concert.
Oh.
Okay. What does non-decreasing mean? That means the first term is less than or equal to the second term, which is less than or equal to the third term. Do you see where I'm going?
Okay, so it has to be both.
So, like the Fibonacci sequence is monotonic. It is non-decreasing because it goes 1, 1, 2, 3, 5. Do you see what I'm saying here?
Oh, yeah. I think that's what you're throwing out.
So if you had a sequence that was just 1 to the n minus 1 to the n, would that be a monotonic sequence?
Yes.
It would be the best sequence because it converges to 1.
I think we talked long enough about how someone just randomly mentioned 21. Are you like running a secret card counting club? Like,
What's 21? About what?
Okay. Now, we can also talk about being bounded. We can be bounded above. What would that mean? If we're bounded above, then all of our terms are,
Above?
well, all of our terms would be less than or equal to some number. Okay?
Don't bring out the Greek letters.
It's not a Greek letter. It's a math symbol for all.
Well, what type of letter is it?
So it's an upside down A.
Yeah, well, I guarantee
It's
it's
actually
been
upside down W's.
How is it an upside down W?
Not a W.
Dave was looking at the M. I was trying to be funny.
Thank you, Darby.
THM 8.5.
Okay, if a sequence is monotonic and bounded, then it converges. Yeah, theorem 8.5. It's really 9.5. They're both changed, but that's fine.
Well, how can it be
So monotonic means non-increasing or non-decreasing. So it's moving, right? And bounded, then we're going to have conversion.
Well, how could it be monotonic and non-bounded?
Well, it could be,
You know, like the first one, like the 1, 2, 4, 8.
Like 2, 4, 6, 8, 10, 12, 14, 16, 18. That would not be counted.
Oh, okay.
All right, so let's get to the fun stuff here. Okay? We need to be able to show whether we have increasing or decreasing sequences. And there are 3 different ways that we're going to be able to do that. There's what we call the difference test. If I want to show that a sequence is increasing, then our difference between like a term and a term before it would need to be what? Yes. Oh, let's go ahead and which means if the difference is negative, we would have what kind of sequence?
Decreasing.
Okay, thank you. Our next is what we call the ratio test. If I take a term divided by the term before it, it would be increasing if that ratio was bigger than 1.
Oh, it's so close.
Okay, Joe?
My legs are very sore
Oh, okay.
on Tuesday.
Okay. And then the derivative. What? This is like the easiest. If the derivative is always positive, then we have an increasing function. Or, excuse me, well, we would have an increasing function, but specifically here, an increasing sequence. Okay? Change all those signs around, and that's how we would prove decreasing. Yes.
That was my
Yep.
That was my question.
Good. Do you want to write those down?
I am writing them down.
Do you want to write down the decreasing ones, or do you want to just infer that we switch the signs?
Oh,
That's
test.
because I can show them. Now, this may seem pointless at the moment, but we do have a couple of our series tests that we will need to know if we have an increasing versus decreasing sequence. So this is where we practice. Okay? I'm going to give you a sequence, and we are going to practice all 3 types of tests.
Yay.
Okay? Our sequence is n over n plus 1. Okay. We will first start with the difference test. The difference test, we need to look at a sub n plus 1 minus a sub n. So a sub n plus 1 would be n plus 1 over n plus 2. And we would subtract a sub n, which is n over n plus 1.
Wait, wouldn't it still be over? I don't get why you just can't do a sub n minus a sub n minus 1. Because they're the same thing.
They are the same thing. Okay, it's basically the term minus the term previous. Okay, this just keeps everything positive. You don't want to say a sub n minus 1 necessarily, because you don't want to go like too far to the left. Okay, now if we're going to subtract fractions, what do we need?
Common denominator.
Okay, so we have n squared plus 3n plus 2. Oh, no. Sorry. Plus 2n plus 1, isn't it? multiply this one by n plus 1 over n plus 1. This one by n plus 2 over n plus 2. Okay? If we go ahead and subtract to combine everything together,
You get 1 over
To the still be 0.
so these cancel. Good. So we get 1 over our common denominator. And see, this is why we keep it with the n plus 1 and n. So we can always see what's going to happen. This, since we have n will always be positive integers, no matter what happens, this is always positive. Which means what kind of function, or excuse me, what kind of sequence do we have? If we could identify this to be always negative for all n's, then we would say that it would be a decreasing function. Sequence. Yes.
Are we going to be only working with always increasing or always decreasing? Or is it going to be like parts?
I would say that not 100% of the time will we have always decreasing, always increasing. Okay? However, for what we're going to do here, we're always going to have that clear sign. Okay? All right, let's talk about the ratio test. With the same sequence. Our ratio test, we're going to look at a sub n plus 1 over a sub n. Okay. In this case, we would have n plus 1 over n plus 2 divided by n over n plus 1. Okay. Well, if we do our multiply by the reciprocal for our division, we would have n plus 1 times n plus 1 over n plus 2 times n. Is this obvious? It is obvious that this fraction is greater than 1.
Yes, it's
What did I write over here? Okay, good. Yes, it is greater than 0, but we need to know that it's greater than 1. Okay? If it was less than 1, then we know we would have a decreasing sequence.
Well, the numerator will always be greater than the denominator by exactly 1.
That is true.
So it's like,
And that's how we know. And that's what I'm saying. It needs to be pretty obvious, right? You don't want to have to, like, do more math to show me that it's true. It's obvious to our
that's what I
eyes.
was going to ask.
What?
Greater than
That's
or equal to,
exactly-
or just greater than?
Just greater.
But if
That's always 1.
that's
No.
exactly when you have to be greater than.
It's not always 1. Depending on what number you plug in, it's different.
These do not cancel.
Oh, yeah. Sorry.
It would only be 1 if you plugged in 0, which isn't a number you're allowed.
Let's talk about the derivative test real quick.
Yay!
If we said that f of n is n over n plus 1, our derivative would be would be 1 over n plus 1 squared, which is always positive. We can tell. We don't have to do anything to prove that it's always positive. We can see it. It's obvious. So this would prove a sub n is increasing. It has to be obvious in all three scenarios, which is why one test may be better than another. You might do the derivative test and you're not really sure. Okay, so maybe a different test would be better. Or like you have a factorial, you can't really take the derivative of a factorial. You can't use the derivative Also, get used to a lot of factorials in our work.
What, things like to the power of n?
No, like,
No, and exploration.
Oh,
So you're really
factorial.
My
excited about
phone
the
will
end.
calculate factorials, even if you give it decimals.
Where are you
It's
going?
kind of weird.